Thank you. Okay, good afternoon everyone. So let's fix the issues we had last time and let's complete the proofs, right? So we are in the process of proving theorem 7.5. Recall that 2 and 3 are equivalent is something we already know by Balash's result, which we have already proved. This was theorem 7.8 star. So 7.8 is actually the same for bricks, and what we proved was for all matching cover graphs. But as I said, it actually works for all matchable graphs. You just need to generalize the definitions. Yeah. So 2 and 3 are equivalent is clear, which basically means that if your perfect matching polytope is indeed a proper subset of the fractional perfect matching polytope, then that is precisely because there is an odd conformal bicycle in the graph, right? And vice versa. One direction is of course easy. If there is a conformal odd bicycle, it's clear. You just construct a vector and you are done. The other direction was a bit trickier. We got a bunch of odd cycles, vertex disjoint, and then we had to bring down the number to 2. And of course, to prove the other direction, we use the characterization of extreme points of the fractional perfect matching polytope, right, which is on your assignment exercises. Okay. So what remains is proving 1 and 2 are equivalent, and we started 2 implies 1 last time, but we did not complete it. Right. So we're proving the contrapositive. Let's suppose the graph G is not solid. Which means that there is a non-trivial separating cut. And from here, we need to somehow prove that the graph is not Birkhoff or Neumann, which means that the perfect matching polytope is indeed a proper subset of the fractional perfect matching polytope. Right? This is where we need to go, and as I said, we will do something slightly more general. We will go to all matching covered graphs and we'll prove something more general which will imply what we want. So let's just do that, and I'll also point out the exact mistake I made last time. So what we'll prove more generally is we've considered a matching covered graph G . And we will assume that G has a separating cut that is not tight. Let's say we call this cut C. A separating cut that is not tight. Now what we'll do is we'll construct a vector a non-negative one regular vector such that it will violate some Edmonds constraint. Which Edmonds constraint? The one for C. X of C is less than 1. And this is precisely where I made the mistake. I said that doing this implies something, and that something was false. Right? So this, if we do this, this will imply. So we have a non-negative one regular vector. Recall that one regular means for every tight cut the sum is equal to 1. If C is any tight cut, x of D is any tight cut, then x of D is equal to 1. Right? And that means that this is precisely the tight cut perfect matching polytope. Non-negative one regular vector. So what we will get is that X belongs to the tight cut perfect matching polytope, but it does not belong to the perfect matching polytope. Therefore, the perfect matching polytope is a proper subset of the tight cut perfect matching polytope. What I wrote last time was, this fellow is a proper subset of the fractional perfect matching polytope. That's not right. Yeah? Good. And if we do this here, then observe that it implies what we want, because in the case of bricks, these two are equal. Right? And in particular, we will have this, which is what we want. Yeah? So this means that the graph is not Birkhoff von Neumann because of this part. So not solid implies not Birkhoff von Neumann. Yeah? Questions, concerns, everything okay? Yeah? So this is now what we need to do in the more general setting. We need to construct such a vector, right? And this is what I left as a TIY last time, or DIY, whatever. Yeah. So anybody figured that out? No, nobody figured it out. Looks like there's someone. No, maybe not. Okay. So let's do it. So we have a separating cut that is not tight. So not tight means there exists a perfect matching M naught such that M naught intersection C is greater than 1, therefore at least 3. And it is a separating cut, therefore, which is equivalent to saying for every edge of the graph there exists a perfect matching ME such that E belongs to ME and ME uses precisely one edge from the cut C. The hint was use all of these to construct the vector X. Okay, try it now. Use all MEs, one for each edge of the graph, and M naught to construct X. Note that you can't take a convex combination of perfect matchings. Okay? You shouldn't take a convex combination of perfect matchings. That will not work, because that will be in the polytope by definition. Therefore, it will not satisfy X of C is less than 1. So, you have to do something that is not convex. But it should still give you a non-negative one regular vector. How will it give you one regular? The coefficients must add up to, if you want a one regular vector, by adding the bunch of perfect matchings multiplied by some lambdas, but you want the final vector to be one regular, your coefficients must add up to 1. You all agree? The coefficients must add up to 1. Think about that. Yeah? At every vertex, one regular means, in particular for every vertex, the sum has to be equal to 1. Of course, also for tight cuts. But if you just think about sum has to be 1 for each vertex, how will that happen? That will happen only if these are just incidence vectors of perfect matchings. So it is alpha 1 times 1 plus alpha 2 times 1 plus da 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 da. That will add up to 1 only if the sum of all the alphas or lambdas, whatever your favorite Greek symbol is equal to 1. So your coefficients have to add up to 1. That is clear. And it cannot be a convex combination because you want x of c is less than 1. That is a further hint. Yeah. give you a hint. One more hint. Try to not tie yourself too much to one regularity. Just get something that is non-negative and regular. Okay? If you have non-negative and regular, then you can just scale to get one regular. Right? If it is R regular, you can just scale. So just try to get something that is non-negative and regular. And largely regularity comes for free. If you take one perfect matching times 17, another perfect matching times 49, you have a regular vector. Because perfect matching is one regular. So in some sense you don't even need to worry too much about regularity. You have to worry about non-negativity. And that is where you will find this useful. Because non-negative means for every edge E, xe is greater than or equal to 0. So that's the reason for using all MEs. I'm not saying you can't do it using a smaller subset of this, but once you see the all MEs solution, you will not want any other. Right, so one thing is clear from here, that you have to use some negative coefficient, right? Because all the coefficients add up to 1. If they are all non-negative, then that's a convex combination. You definitely have to subtract something. Without subtraction, it's not going to work. Right? You have to add up a bunch of things, but of course you don't want to subtract too much, because you need the final vector to be non-negative. So with subtraction you should be very conservative. With addition you don't really care. In some sense, worrying about fractions is not a good idea. Just use integers. Just add a bunch of things, subtract something. You know you need to subtract something for sure, right? And then see if whatever you tried satisfies this hint. Right, so one thing that is, since I have said use all the MEs, we know we have to subtract something for sure. One natural thing to try is sum up all the MEs. I'm just going to write ME, which basically means chi ME. I won't write that. Sum up all the MEs and subtract M naught. Analyze this. Does this satisfy this hint? Think about that. Supposing your graph has 20 edges. Think about the sum at each vertex. I like the number 20. When I was doing it, I tried 20. Doesn't really matter. Supposing my graph has 20 edges, what will be the sum at each vertex? So this is my y. Every matching is just a one regular vector. The sum at each vertex in a perfect matching, sorry. In a perfect matching, the sum at each vertex is equal to 1. So if you add up 20 perfect matchings, doesn't matter which edge each perfect matching uses. The sum at each vertex will be 20. Right? And now you are subtracting one perfect matching. Sum will become 19. You agree? Yeah? Right? So the sum at each vertex is 19. So it is a 19 regular vector if my number of edges is 20. Yeah? And is it non-negative? That's the tricky part. That is where this really helps you. Consider any edge of the graph. Well, how can it become negative? It can become negative only because of this fellow, if it is used here. Well, good news is it was used at least in one perfect matching here, because this is summation over all edges, right? And the ME contains E. So every edge was used at least once in this summation. So it will be at least once because of this. And here you will subtract. Well, it's a perfect matching. It can only use an edge once. So it will be subtracted. It will become 0. It is still non-negative. It can't become negative. So convince yourself that if my number of edges is 20, then this is 19 regular and non-negative. Well, now you can make it 1 regular. Divide by 19, right? That's it. So that's your thing. Your x is simply 1 by m minus 1 times this expression. Yep. Sum of all the MEs, of course I mean the chi ME minus chi M naught, and then divide by m minus 1. That's it. This is a and now of course we need to check why this is less than 1. Well, we could have done that actually here y for y itself. Let us check that y of c is actually less than 19 in our example. Let's check this. Right? Why is this true? So you have to think about ME intersection C and M naught intersection C. Right? Observe that ME intersection C is at least 1 for each ME, because C is an odd cut. So each of these will contribute at least 1. I have 20 perfect matchings, so I will get 20 over here. Oh, in fact it will be equal to 20 because ME intersection C is equal to 1. Yeah. So in fact this will contribute 20 to the cut C. But then I'm subtracting at least 3. So I got 20 minus 3, 17, which is less than 19. When I divide by 19, I have what I want. X of C is less than 1. Yeah. So because this is true, we also conclude that X of C is less than 1. So we have a non-negative, 1 regular vector that satisfies the desired property. We are done. Yeah. Hopefully you see the power of separating cuts. Right. This characterization may seem kind of useless when you first see it, like, yeah, whatever. But now you see how useful it is. Okay, so we are done with this direction. Questions, concerns? All good? Yeah? Okay, so what we have done is we have proved in the more general setting that once you have a separating cut that is not tight was very crucial, right? Because of this. Then we concluded that the perfect matching polytope is indeed a proper subset of the tight cut perfect matching polytope. In the case of bricks, this implies that the perfect matching polytope is a proper subset of the fractional perfect matching polytope, right? And therefore the brick is not Birkhoff or Neumann. So not solid implies not Birkhoff or Neumann. Now we need to prove the other implication, right? For that we will focus on bricks. Alright, so I will maybe erase this stuff. Okay. Alright, so we are done with this. 2 implies 1 is done. Once again, let's consider the contrapositive. Supposing the brick under consideration is not Birkhoff von Neumann, then you want to show that it is not solid. Right? So that means that we have to show the existence of a non-trivial separating cut in G, right? Because that's what it means to be not solid for a brick. But what we have is not Birkhoff von Neumann. Yeah. It's kind of far away. But well, what does not Birkhoff von Neumann mean? It means that the perfect matching polytope is a proper subset of the fractional perfect matching polytope. Yeah. In particular, there is an element here that is not here. Let's take such an element. Let X be some element, some vector in the fractional perfect matching polytope that is not in the perfect matching polytope. Well, fractional means it is non-negative and one regular. Well, this is a brick, so one regular is good enough. It's the same as degree constraints. Right, so I have a non-negative one regular vector, right? No, this one is about bricks. Here we are not considering matching choreographs. It is only for this implication that we went to the more general setting. Here we are back to a brick. Yeah. So yeah. So thus X is non-negative and one regular. But because it is not in the perfect matching polytope, it must violate some Edmonds constraints by Edmonds theorem. Right? This is by Edmonds theorem 6.1. So, well, I mean, so there's a non-trivial odd cut in the graph for which x of c is less than 1. Right? That's what it means. This implies that there exists a non-trivial odd cut C such that x of c is strictly less than 1. And it would be nice if you could just say, hey, C is a non-trivial separating cut, or C is a separating cut, it's already non-trivial. If you can just somehow prove that C is a separating cut, that would be great. But life is not always so easy. Turns out there exists a C for which this is actually separating. So we need to somehow find that needle in a haystack, right? So the goal is to show existence of a non-trivial odd cut D, or maybe I'll just call it C, fine. C such that x of C is less than 1 and at the same time C is a separating cut. This is what we will do. Amongst all the non-trivial odd cuts that satisfy this, that violate Edmonds inequality, we will show that there is one that is actually a separating cut. Right. The way they do it is they use a certain relation on the cuts. They define a certain relation on the cuts. They call it the precedence relation. And then they use a precedence relation to choose a C and show that this C actually works. But I don't want to directly tell you what the precedence relation is. So maybe I'll just, we'll just see the precedence relation. We'll kind of try to bring it up in the discussion. Right? So let's just take an arbitrary non-trivial odd cut for which x of C is less than 1 and let's see what happens. I mean, if it is not separating, then one of the C contractions is not matching covered. And then we will see what to do. Yeah. And hopefully that will naturally lead us to the precedence relation rather than me just throwing the precedence relation at you. Okay. Maybe I'll get rid of this. 2 implies 1 is done. Okay. So, proof attempt. Continued from here. Let's pick an arbitrary non-trivial cut for which x of C is less than 1. Did I say odd cut? Yeah, odd cut. And let's say C is partial of y. Yeah. Let's consider the 2C contractions. G1 is G shrink y bar and G2 is G shrink y. If both of these are matching covered, we are done. So let us suppose one of them, at least one of them, is not matching covered. Is it connected? G1 is connected, or can it be disconnected? Connected, right? If G1 is disconnected, then G will be disconnected. You've just shrunken a set of vertices into a single vertex. Every cut of G1 is a cut of G. Yeah, connected is clear, right? Yeah. So therefore, if it is not matching covered, either it is not matchable or it has an edge that is not matchable. Or G1 is matchable but has a barrier that is not stable. Should I call it unstable? Maybe not. Yeah. Okay, let's make some drawings and see what happens. So let's consider the case where G1 is not even matchable. So that means it will have a touch set. S. Let's say I have 5 vertices without loss of generality. Why not? And let's say I have 7 or more odd components. Yeah? Even number of vertices. So I can draw at least 2 more odd components. Right? Supposing this is happening in G1. Where is the shrunken vertex? Shrunken vertex is little y bar. Where is the shrunken vertex? Yes, in the set S, the touch set. Yeah, everybody see that? The shrunken vertex has to be in S, otherwise this would be a touch set in the original graph, right? So, yeah, this is the situation in G1. I want you all to have 2 graphs in picture. G1, which I have drawn, and I also want you to be able to imagine G. His y bar just blows up into a capital Y bar. Right? Try to keep both of these in mind. I will not draw the other one. Yeah. Okay. Now for all the odd components of G1 minus S, I want you to think about so let's say J is an odd component of G1 minus S. So let's say J is this, for example, right? But J could be any odd component. So try to think of each of them in some sense. What can you say about X of partial of J? And here I am using a shorthand notation. By partial of J, I mean partial of vertex set of J. Yep. So I want you all to think about this for all odd components, right? And see if you can arrive at some conclusion. Okay, let me know if you have some thoughts. While you are thinking, I'll also make a drawing of the other situation where the graph is matchable but it has a barrier that is not stable. This is one situation. The other situation is graph is matchable. It has a barrier that is not stable. And do you all agree that once again we can conclude that the shrunken vertex is in the barrier? Yeah, right? If it is not in the barrier, then this would be a unstable barrier, if I may, in the original graph. That's a problem, right? So, even in this situation, y bar has to be here. Of course, it may be incident with one such edge. I am not trying to imply anything about this, right? So, there could be edges incident with y bar. We know there is at least one edge in the barrier, which may or may not be incident at y bar, right? So, yeah. Okay, so these are the two situations we need to deal with. And in both of these situations, I want you to think about this stuff. Take any odd component of G1 minus S, even in that graph, in that drawing, and think about x of partial of J. And think about all of them at the same time, also about individuals. Right. Alright, maybe we can take a short break here and we can resume after the break. Yeah. Thank you.